Today, we secure our web traffic with heavy cryptography, but the protocol that actually routes that traffic across the internet, the domain name system, still operates natively in clear text. It's the equivalent of locking a document in a steel vault and then carrying that vault across the street in a transparent glass briefcase. To understand why, we have to look back to the baseline architecture of DNS, defined in RFC 1034 in 1987. The engineers who built the system were solving for explosive network growth. They designed a globally distributed database that prioritized extreme availability and rapid scalability. Privacy was simply not a design parameter. Because of this, standard DNS queries broadcast over port 53 using User Datagram Protocol, or UDP. Every request is sent entirely unencrypted. This open broadcast exposes two critical pieces of data to anyone listening on the network: the source IP address of the user and the queue name, the exact domain name being requested. This legacy clear text architecture creates a structural vulnerability. Anyone with network path access, an internet service provider, a network admin, or an eavesdropper can monitor your exact intent and browsing habits before a secure TLS connection is even established. Fixing this presents a profound structural challenge. You have to retrofit modern cryptography onto a deeply entrenched, globally distributed database, and you have to do it without breaking foundational internet routing. To patch this vulnerability, the Internet Engineering Task Force proposed two distinct standards: DNS over TLS, known as DOT, and DNS over HTTPS, known as DOSH. Both of these protocols utilize transport layer security to encrypt the DNS queries. However, their methods of encapsulating and routing that data are entirely different. The choice between DOT and DOSH is a structural decision. It dictates the balance of power between local network administrators who want visibility and end users who want privacy. To see exactly what needs to be encrypted, we first need to map the DNS tree hierarchy. The domain name system is a distributed database that flows downward, starting at the root zone. The core unit of this database is the resource record. When you type a web address, you are usually looking for an A record, which contains the exact IP address, or an NS record, which points to the authoritative name server for that domain. This diagram illustrates the resolution process. It begins with the first mile, where a client device asks a recursive resolver to find a specific domain. The client's request is recursive. It expects a final answer. But the resolver's job is iterative. It must hunt down the answer by querying multiple servers in sequence. The resolver starts by querying the root server. The root doesn't know the exact IP, so it refers the resolver downward. Next, the resolver queries the top-level domain server, like .com or .org, which provides another referral. The resolver finally queries the authoritative zone for that specific domain. This server holds the exact A record. The resolver takes that IP address and returns it to the waiting client. Traditionally, every single hop in this hierarchical database occurs in clear text over unencrypted UDP or TCP connections. Upgrading every authoritative server on Earth simultaneously is impossible. Therefore, modern encrypted DNS standards focus entirely on locking down that first-mile connection between the client and the resolver. The Internet Engineering Task Force specified DNS over TLS, defined in RFC 7858, as the first major mechanism to secure this vulnerable first mile. In this diagram, we can see the encapsulation strategy. The client directly encapsulates the DNS data payload into a transport layer security wrapper. Before any data moves, the client and server must perform a TLS handshake. They exchange hello messages, verify digital certificates, and derive a shared session key to encrypt the data. Once encrypted, DOT routes the traffic off the legacy port 53 and assigns it to its own dedicated port, port 853. Using a dedicated port has a specific network implication. While the payload itself is encrypted and unreadable, the traffic is still explicitly identifiable as DNS traffic because of where it's routed. This is highly preferred for enterprise environments. It allows network administrators to isolate, monitor, and enforce routing policies on DNS traffic right at the firewall. DNS over TLS successfully secures the query from eavesdropping, but it deliberately broadcasts the presence of that traffic to maintain organizational network control. A completely different philosophy emerged with RFC 8484, DNS over HTTPS, or DOSH. Look at this adjusted protocol stack. In DOSH, an HTTP layer is inserted between the DNS payload and the TLS encryption layer. The client formats the DNS query as a standard HTTP GET or POST request, using the specific media type, application/DNS message. The client then uses a DOH Uniform Resource Identifier, or URI, to point that HTTP request to the correct resolver namespace. Because the request is formatted as HTTP and encrypted with TLS, it travels over the standard port for secure web traffic, port 443. This single routing decision completely camouflages the DNS resolution process. DOH queries blend seamlessly into a rushing river of high-volume web browsing traffic. This provides a distinct tactical advantage for end users. DOH effectively bypasses DNS-based censorship because a firewall cannot block port 443 without breaking the entire modern web. DOH is engineered to prioritize absolute end-user privacy, intentionally overriding with visibility and control of local network administrators. This matrix illustrates the trade-off when traffic hits a corporate firewall. DOT is built for network control. DOH is built for privacy. The enterprise firewall easily separates and inspects port 853 traffic, but port 443 passes through completely uninspected, looking like any secure web page. When users manually configure modern browsers to use public DOH resolvers, organizations instantly lose the ability to apply DNS-based malware filtering or parental controls. To regain sovereignty, administrators have to deploy tools like PowerDNS, DNSDist, to host their own internal DOT and DOH resolvers, forcing enterprise endpoints to use company-controlled encryption. The technical mechanics of encapsulation ultimately dictate who owns the metadata of your internet journey. However, both DOT and DOH leave a critical gap in the security stack. They encrypt the transport connection, but they do not verify the authenticity of the data itself. A perfectly encrypted TLS connection to a compromised or spoofed resolver still results in cache poisoning and misdirection. You securely receive a fraudulent IP address. This is where DNS Security Extensions, or DNSSEC, comes in. DNSSEC adds digital signatures to the DNS responses, proving data origin authentication and protecting the integrity of the record. Encryption prevents eavesdropping, while authentication prevents tampering. To fully secure the protocol, you need both. But modern privacy carries a performance cost. The TCP connections and TLS handshakes required by DOT and DO add notable latency compared to the incredibly lightweight UDP architecture from 1987. To resolve this, engineers have proposed a next-generation standard, DNS over QUIC, defined in RFC 9250. By returning to UDP transport, DOC combines the security of TLS 1.3 with the low latency and response times the original DNS architects intended.